Chemical reactions are rarely a one-way street. In closed environments, products you create can spontaneously break apart and revert back into original ingredients. Take the synthesis of ammonia. You combine nitrogen and hydrogen, but the equation is linked by a double-sided equilibrium arrow. As the forward reaction produces ammonia, the reverse reaction breaks it down. Eventually, the rates of these two competing reactions match. This is dynamic equilibrium. The microscopic reactions haven't stopped, but the net generation of ammonia drops to absolute zero. If your goal is to manufacture millions of tons of fertilizer, accepting this natural thermodynamic stall guarantees failure. You have to break the limit. Industrial chemical synthesis works by weaponizing this natural balance, actively forcing closed systems into a state of disruption to extract continuous yield. The theoretical framework for achieving this was cracked in the early 20th century by chemist Fritz Haber. But it was engineer Carl Bosch who scaled Haber's thermodynamic theories into towering, high-pressure manufacturing plants. Their work relied entirely on Le Chatelier's principle, the chemical rule stating that if a closed system at equilibrium is subjected to an external stress, it will shift its position to counteract that stress. By simultaneously manipulating three exact physical variables, pressure, temperature, and concentration, engineers perpetually disrupt this balance and force the system to maximize ammonia production. To understand the disruption, we must first establish an unstressed, closed system baseline reactor filled with isolated nitrogen and hydrogen molecules. This diagram shows the forward kinetics. As these gases mix, collisions occur. Nitrogen and hydrogen bind together, successfully forming clusters of ammonia. But without external stress, those new ammonia clusters dissociate. They break apart back into nitrogen and hydrogen at the exact same rate they are formed. Mathematically, the reaction quotient, Q, has caught up to the equilibrium constant, K. The system is perfectly balanced. Le Chatelier's rule dictates that to change this zero-sum outcome, we must introduce a physical stress that the system is forced to resolve. An unstressed system yields nothing. We have to squeeze it. The first variable of manipulation is severe pressure. Look at the stoichiometry of the reactants. 1 mole of nitrogen gas and 3 moles of hydrogen gas equal 4 total moles of volume. On the product side, the resulting ammonia gas only takes up 2 moles. When we mechanically compress the reactor walls, we drastically reduce the available volume. This creates a sudden spatial crisis. The system is under immense volumetric stress due to spiking gas density. It resolves this stress according to Le Chatelier, immediately favoring the reaction producing fewer gas molecules to physically take up less space. The equilibrium position shifts heavily to the right, driving ammonia production upward. There are rigid structural limits here. Even dense steel pipes have a threshold before the atmospheric pressure causes a catastrophic failure. Even at the limits of material engineering, pressure alone leaves too much unreacted gas in the chamber. Pressure cleanly exploits the stoichiometry, but to push the yield further, we have to introduce a second point of stress. Our second variable of manipulation is temperature. This equation illustrates that the forward reaction is exothermic. It releases heat as a physical byproduct. Applying Le Chatelier's logic, if you deliberately lower the temperature, the system will try to replace that missing heat by producing more ammonia. But we run into a kinetic paradox. The third and most crucial manipulation is a shift in concentration. A truly closed system is inherently flawed. If ammonia accumulates inside the tank, the reverse reaction will inevitably speed up and stall the entire process. Engineers solve this by building a continuous extraction mechanism. A condensation pipe actively siphons away liquid ammonia as soon as it forms. The closed system becomes an open loop. It extracts product from one end while simultaneously injecting fresh nitrogen and hydrogen into the other. This prevents the concentration from ever balancing out. Because the ammonia is constantly siphoned away, the system senses a permanent deficit on the product side of the equation. Le Chatelier's final consequence takes over. The system frantically shifts the reaction forward to replace the constantly missing ammonia. Because the product never accumulates, the mathematical condition for equilibrium is permanently avoided. Q never equals K. Compare this high-velocity open loop to the static stalled chamber we started with. Continuous concentration shifting forces the system to perpetually chase a balance it is never allowed to achieve. Stepping back from the kinetic theory, we can observe how these specific microscopic manipulations scale to macroscopic engineering. This continuous loop of extreme pressure, optimized heat, and constant extraction requires massive physical infrastructure. The final equilibrium position is dictated by the precise, simultaneous application of all three thermodynamic stresses. This synchronized pressure and extraction cycle yields the stabilized, highly efficient output that defines modern manufacturing. Abstract chemical theories function as the literal blueprints for designing industrial architecture. The output of this thermodynamic manipulation dictates global agricultural yields and chemical supply chains. Every bag of fertilizer represents ammonia that the laws of physics, left to their own devices, would never have allowed to accumulate. Mastering equilibrium through Le Chatelier's principle turned a stalling laboratory reaction into the foundation of modern chemical synthesis.